When people imagine the most dangerous place in the universe, the answer seems obvious. A black hole, a region where gravity becomes so powerful that once something crosses a boundary called the event horizon, escape becomes impossible. Not even light can return. For decades, black holes have symbolized the ultimate cosmic danger, but the truth is more surprising. At a safe distance, a black hole is not chaotic or explosive. It behaves in a predictable way, much like any other massive object in space. If our Sun were magically replaced by a black hole with the same mass, Earth would continue orbiting almost exactly as it does today. Gravity would still hold the planet in its path. The real danger appears somewhere else. Astronomers studying extreme cosmic environments began noticing a pattern. The most violent places in the universe are not defined by a single object. They emerge when several powerful forces combine at once. Gravity becomes overwhelming. Radiation floods surrounding space. Magnetic fields accelerate particles to enormous energies. Temperatures rise to millions of degrees. Where these forces overlap, the universe becomes capable of sterilizing entire planets from thousands of light years away. The scientific understanding of these environments began with the work of Albert Einstein in 1916, when the theory of general relativity revealed how mass bends space-time itself. Decades later, astronomers began discovering the real objects created by those equations. They found collapsed stars denser than atomic nuclei, magnetic fields strong enough to distort matter, explosions capable of briefly outshining entire galaxies. These discoveries revealed something profound about the universe. The most dangerous places in the cosmos are not simply locations, they are processes, and many of them begin with the same dramatic event, the violent death of a massive star. Because when a star far larger than our Sun reaches the end of its life, gravity takes control in a matter of seconds. The result is one of the most powerful explosions nature can produce, a supernova. And inside that explosion, the universe creates objects so extreme that they reshape our understanding of physics itself. In the next chapter of this story, we follow the moment when a star dies, and something far more dangerous is born. Every star in the universe is fighting a quiet battle. For millions or even billions of years, gravity pulls inward, while nuclear fusion pushes outward. This balance keeps a star stable, glowing steadily in the darkness of space. But the balance is temporary. Eventually, the fuel that powers the star begins to run out. For small stars like our Sun, this process happens slowly. But the most massive stars live very different lives. Some burn through their fuel in only a few million years, a brief moment on the cosmic timeline. When the fuel finally disappears, something dramatic happens. The outward pressure that once held the star up suddenly weakens. Gravity, which has been patiently pulling inward for the star's entire life, finally wins. The collapse begins instantly. In less than a second, the core of the star falls inward at thousands of kilometers per second. Layers of stellar material rush toward the center, compressing matter to densities that push the limits of physics. Astronomers began understanding this violent process in 1939, when theoretical physicists studying stellar evolution realized that gravity alone could crush a dying star's core beyond anything seen in normal matter. Their calculations showed that once collapse begins, nothing inside the core can stop it. The imploding material slams into the ultra-dense center and rebounds outward. A shock wave tears through the star, blasting its outer layers into space. The explosion that follows is called a supernova. For a brief period, a single exploding star can release as much energy as an entire galaxy of billions of stars. Light from the blast spreads across space, while debris expands outward at thousands of kilometers per second. These explosions are so bright that astronomers have recorded them in distant galaxies millions of light years away, but the explosion itself is only part of the story. Because after the outer layers of the star are blown away, the collapsed core remains. Inside that tiny region, gravity compresses matter so intensely that atoms themselves can no longer exist in their normal form. The universe begins to create something entirely new, objects smaller than a city, yet heavier than a star. Objects where matter is packed so tightly that a single teaspoon would outweigh entire mountains. These objects are called neutron stars. and their existence revealed that the death of a star does not simply end a stellar life. Sometimes it creates one of the most extreme environments in the cosmos. But even neutron stars are not the final stage of this story, because under certain conditions, these collapsed remnants evolve into something even more powerful. Objects capable of reshaping matter itself, and that discovery would lead astronomers to one of the strangest forces ever measured in the universe. Imagine compressing something as massive as our Sun into an object barely wider than a large city, not shrinking it gently, but crushing it so violently that the structure of atoms themselves collapses. This is not science fiction. It is one of the most extraordinary objects ever discovered in the universe: a neutron star. The idea first emerged in the early 20th century, but it became scientifically real in 1967. That year, graduate student Jocelyn Bell Burnell, working at the University of Cambridge, detected an unusual radio signal coming from deep space. The signal arrived with astonishing precision, every 1.337 seconds. At first, the regularity of the signal seemed almost impossible. Natural cosmic sources rarely behave like a perfectly ticking clock. Some researchers even briefly considered the possibility of artificial transmissions. But, as more signals were discovered, the explanation became clear. These pulses were coming from rapidly rotating neutron stars, collapsed stellar cores left behind after supernova explosions. A neutron star forms when gravity squeezes the core of a dying star so intensely that electrons and protons are forced together. The result is matter made almost entirely of neutrons. Normal atomic structure disappears. What remains is a sphere only about 20 kilometers across, yet containing more mass than the Sun. The density is almost beyond comprehension. If a fragment the size of a sugar cube could somehow be brought to Earth, it would weigh hundreds of millions of tons. Gravity on the surface is equally extreme. An object dropped from 1 meter above the surface would strike the ground faster than most bullets travel on Earth. Many neutron stars spin incredibly fast. Some rotate hundreds of times every second. As they spin, beams of radiation sweep through space like lighthouse signals. When one of these beams crosses Earth, radio telescopes detect a pulse. These objects are known as pulsars. Their discovery provided the first direct evidence that stellar collapse can produce environments far more extreme than ordinary stars. Yet neutron stars are not the final step in this chain of cosmic violence, because in rare cases something even stranger happens. Inside a few of these objects, magnetic fields grow to unimaginable strength, fields so powerful that they can distort atoms themselves. These objects are called magnetars, and they represent some of the most dangerous places known in the universe. In most places in the universe, magnetism is subtle. It quietly guides compass needles, shapes auroras, and protects planets from charged particles. But there exist places where magnetism stops being gentle. It becomes destructive. In the early 1990s, astronomers studying strange bursts of gamma rays noticed something unusual. Several neutron stars were releasing sudden flashes of extremely energetic radiation that did not match the behavior of ordinary pulsars. These events were detected by high-energy observatories, including NASA's Compton Gamma Ray Observatory. The signals were brief, violent, and unpredictable. In 1992, astrophysicists Robert Duncan and Christopher Thompson proposed an explanation that seemed almost unbelievable. They suggested that some neutron stars possess magnetic fields so strong that they dominate the physics of the star itself. These objects became known as magnetars. To understand their power, consider the magnetic field around Earth. It is strong enough to guide satellites and protect our atmosphere from the solar wind. A refrigerator magnet in your kitchen is already hundreds of times stronger. A magnetar is something else entirely. Its magnetic field can reach about 10 to the 15th power Gauss, roughly 1 trillion times stronger than Earth's field. At that strength, magnetism begins to interfere with the structure of matter. The electrons that normally move in smooth clouds around atomic nuclei become squeezed into narrow shapes. Atoms themselves stretch and deform under magnetic stress. The neutron star's crust, a rigid shell only a few kilometers thick, cannot withstand that stress forever. Eventually it cracks. Astronomers call these fractures starquakes. When they occur, enormous magnetic energy is suddenly released as intense bursts of X-rays and gamma rays that race across the galaxy at the speed of light. One such burst would later demonstrate just how far that energy can travel, because even from tens of thousands of light years away, a magnetar flare can still disturb a planet's atmosphere. And in 2004, astronomers witnessed exactly that. A single magnetic eruption from deep within our galaxy sent a wave of radiation across space, strong enough to briefly affect Earth itself. That moment revealed something extraordinary about the universe. Even objects thousands of light years away can still reach us with destructive power, and the event that proved it would become one of the most powerful explosions ever recorded from a single star. The story of that explosion begins on a winter day in December 2004. On December 27th, 2004, something remarkable happened in the night sky. Spacecraft orbiting Earth suddenly detected an intense flash of gamma radiation. For a fraction of a second, detectors on multiple satellites were overwhelmed by the signal. At first, scientists were unsure what had happened. Gamma-ray bursts are among the most powerful explosions in the universe, and instruments such as NASA's Rahesii satellite and the European Space Agency's Integral Observatory had recorded a pulse far brighter than almost anything seen before. But this explosion did not come from a distant galaxy. It came from inside our own Milky Way. The source was a magnetar known as SGR 1806-20, located roughly 50,000 light-years away. Despite that enormous distance, the energy released during the flare was so intense that it briefly affected the environment around Earth. To understand the scale, imagine the Sun suddenly releasing in a fraction of a second the amount of energy it normally produces over hundreds of thousands of years. That is roughly the scale of energy astronomers estimated for the magnetar flare. When the burst reached our planet, high-energy gamma rays struck the upper layers of Earth's atmosphere. These photons interacted with atmospheric molecules, briefly altering the structure of the ionosphere, the electrically charged region of the atmosphere that reflects radio waves around the planet. Radio instruments on Earth detected the disturbance almost immediately. For a moment, a stellar eruption occurring halfway across the galaxy had left a measurable fingerprint on our planet. Fortunately, the distance protected us. By the time the radiation travelled 50,000 light-years, it had weakened enough that its effects were limited to the upper atmosphere. But the event revealed something unsettling about the universe. Some cosmic explosions are powerful enough to influence planets across interstellar distances. If the same kind of flare occurred much closer to Earth, the consequences could be far more serious. Intense radiation could damage the ozone layer, exposing the surface of a planet to dangerous ultraviolet light. This discovery forced astronomers to reconsider a profound question. Perhaps the most dangerous places in the universe are not defined by objects alone. They are defined by events, sudden releases of energy capable of transforming entire regions of space. And among those events, few are more powerful than the next phenomenon astronomers would begin to understand. An explosion so energetic that for a few seconds it can outshine an entire galaxy. In the late 1960s, satellites built for an entirely different purpose began detecting something unexpected. Instruments designed to monitor nuclear tests suddenly registered brief flashes of the most energetic light known in nature: gamma rays. These signals were unlike anything scientists had seen before. They appeared without warning, lasted only seconds, and then vanished. Yet in that short moment, they released staggering amounts of energy. The satellites responsible were part of the United States Vela program. Launched to enforce the 1963 Nuclear Test Ban Treaty, the spacecraft carried detectors capable of identifying gamma radiation in space. But by 1967, the instruments began recording bursts that clearly did not originate on Earth. The discovery was announced publicly in 1973 by a research team led by astrophysicist Ray Kleber-Sadel at Los Alamos Scientific Laboratory. The events were named gamma-ray bursts. For decades, their origin remained one of the greatest mysteries in astronomy. Then, in 1997, a breakthrough came from the Italian-Dutch satellite BeppoSAX. For the first time, astronomers were able to pinpoint the location of a burst, and observed the fading afterglow that followed. The measurements revealed that these explosions were not nearby. They were occurring in distant galaxies, billions of light years away. That realization changed everything. Even across such unimaginable distances, gamma-ray bursts were still bright enough to trigger detectors orbiting Earth. The implication was unavoidable. These were among the most energetic events ever observed in the universe. Many gamma-ray bursts occur when massive stars collapse at the end of their lives, forming black holes. As the star's core collapses, enormous amounts of energy are channeled into narrow jets that blast outward at nearly the speed of light. For a few seconds, those jets produce an intense beam of gamma radiation. If one of those beams were directed toward Earth from within our own galaxy, the effects could reach far beyond astronomy. Gamma radiation striking a planet's atmosphere can break apart ozone molecules, weakening the shield that protects the surface from harmful ultraviolet light. The consequences could ripple through ecosystems across land and ocean. Fortunately, such an event would require extraordinary alignment and proximity. But the existence of gamma-ray bursts revealed a profound truth about the universe. Some of its most dangerous events are not confined to a single star. They can release enough energy to affect entire regions of space. Yet there are places where energy is not released in brief explosions, but continuously, environments where gravity, radiation, and magnetic forces operate together without pause. To find those places, astronomers had to look toward the centers of galaxies. At the center of almost every large galaxy lies an object so massive that it controls the motion of millions of stars. For decades, astronomers suspected these regions contained something extraordinary, but proving it required years of careful observation. The breakthrough came in the 1990s and early 2000s, when two independent research teams began tracking the motion of stars near the center of the Milky Way. Using powerful telescopes at the European Southern Observatory and the Keck Observatory in Hawaii, astronomers including Reinhard Genzel and Andrea Ghez measured how these stars moved through space. What they found was astonishing. Several stars were orbiting an invisible object at incredible speeds. One star completed its orbit in just 16 years, while reaching velocities of more than 7,000 kilometers per second. The only explanation was gravity from an extremely compact object containing about 4 million times the mass of our Sun. This object is known today as Sagittarius A star. It is the supermassive black hole at the center of our galaxy. Unlike the brief explosions discussed earlier, the environment surrounding supermassive black holes can remain active for millions of years. When gas clouds, dust, or even entire stars drift too close, gravity pulls this material inward. But the matter rarely falls straight in. Instead, it begins to orbit the black hole, forming a rapidly spinning disk of superheated gas known as an accretion disk. Inside this disk, particles move at enormous speeds. Collisions between them create friction that heats the gas to millions of degrees. At those temperatures, the disk begins to glow with intense X-rays and gamma radiation. From across the universe, these regions can shine brighter than the entire galaxy surrounding them. Astronomers call these powerful objects quasars. The discovery of quasars revealed that black holes do not always hide quietly in darkness. Under the right conditions, they become some of the brightest and most energetic engines in the cosmos. Yet even the blinding radiation of an accretion disk is not the most dramatic feature of these environments. Because sometimes the rotating plasma around a black hole launches enormous beams of energy into space, beams capable of crossing entire galaxies, and anything caught in their path enters one of the most dangerous environments known in the universe. Those beams are known as relativistic jets. In 1918, astronomers studying distant galaxies noticed something unusual. Some galaxies appeared to be launching narrow streams of light far beyond their visible edges. At the time, the observation was mysterious. No known stellar process could explain structures stretching thousands of light years into space. Decades later, with the arrival of radio telescopes and space observatories, scientists finally understood what they were seeing. These streams were not ordinary light. They were immense beams of matter and energy, launched from the regions surrounding supermassive black holes. Today they are known as relativistic jets. The discovery became clear in the late 20th century through observations from facilities such as the Very Large Array in New Mexico and later the Hubble Space Telescope. Astronomers observed jets emerging from galaxies like M87, extending for tens of thousands of light-years into intergalactic space. What powers these enormous beams begins inside the accretion disk around a feeding black hole. Gas swirling around the black hole becomes so hot that it forms plasma, an electrically charged state of matter. Within this rotating plasma, powerful magnetic fields twist and tighten like coiled springs. Eventually, part of that energy escapes along the black hole's rotational axis. The result is a jet. Inside these jets, particles are accelerated to speeds extremely close to the speed of light. Electrons and atomic nuclei race outward while emitting intense radiation across the electromagnetic spectrum, including radio waves, X-rays, and gamma rays. The scale is difficult to imagine. Some relativistic jets extend more than 1 million light-years from the galaxy that created them. A single beam can carry enough energy to heat enormous clouds of gas or disrupt star formation across entire regions of space. If a planetary system were located directly inside such a jet, the environment would become extremely hostile. High-energy particles would bombard the atmosphere of any planet in the region. Over time, this radiation could strip away protective atmospheric layers and expose the surface to intense cosmic radiation. Yet even these enormous beams represent only one part of a much larger pattern. Astronomers began noticing that the most dangerous places in the universe often appear where several extreme forces overlap. Gravity from supermassive black holes, radiation from accretion disks, relativistic jets blasting energy across intergalactic space. When these forces combine, entire galactic regions can become cosmic danger zones, and to understand where such environments are most likely to exist, scientists had to examine the larger structure of galaxies themselves. If the universe were mapped by safety instead of distance, some regions would appear far darker than others. Astronomers gradually realized that extreme cosmic events do not occur randomly. Instead, they tend to cluster in particular environments where gravity, radiation, and stellar activity become unusually intense. One of the clearest examples lies near the centers of galaxies. In 2018, detailed observations using instruments such as the Event Horizon Telescope and long-term stellar tracking by teams led by Reinhard Genzel and Andrea Ghez strengthened our understanding of these regions. Their work confirmed that supermassive black holes dominate the gravitational landscape at galactic cores. But the black hole itself is only part of the story. Galactic centers often contain dense clouds of gas, crowded star populations, and powerful gravitational interactions. When stars orbit this environment, they experience frequent close encounters, intense radiation fields, and the influence of massive objects. In active galaxies, these crowded conditions can feed the central black hole with enormous amounts of matter. Gas and dust spiral inward, forming luminous accretion disks while launching relativistic jets that extend thousands of light-years into space. In such regions, multiple cosmic hazards exist simultaneously. Massive stars form and die rapidly, increasing the likelihood of supernova explosions. Neutron stars and magnetars appear in greater numbers. Gravitational interactions between stellar remnants can produce violent mergers that release bursts of gravitational waves and high-energy radiation. The result is an environment where violent astrophysical processes occur far more frequently than in quieter parts of a galaxy. For any planetary system forming within such a region, stability would be difficult to maintain. Radiation levels could fluctuate dramatically. Nearby stellar explosions might occur within relatively short cosmic intervals. High-energy particles from jets or supernova remnants could erode planetary atmospheres. Compared to these crowded galactic cores, most of the Milky Way is remarkably calm. Our solar system lies far from the center, orbiting within the outer regions of the galactic disk. This quieter neighborhood contains fewer massive stars and far fewer catastrophic events. That distance may be one of the reasons complex life had time to develop on Earth, because the most dangerous places in the universe are not single objects. They are environments where multiple extreme forces combine. And understanding why our planet avoided those environments leads to one final question. In a universe filled with violent regions, how rare is a place safe enough for life to survive? For most of human history, the night sky looked calm. Stars moved slowly across the darkness. Planets followed predictable paths, and the universe appeared steady and unchanging. But over the past century, astronomy has revealed a far more violent reality. Across the cosmos, stars explode, neutron stars collapse into ultra-dense remnants, magnetars unleash bursts of radiation strong enough to cross the galaxy, and supermassive black holes launch jets that stretch for millions of light years. Against this backdrop of cosmic violence, one question becomes impossible to ignore. Why is Earth still here? In the late 20th century, astronomers began studying the larger structure of the Milky Way to understand where life might safely exist. Researchers such as Charles Lineweaver and colleagues proposed a concept now known as the galactic habitable zone. The idea is simple but profound. Not every region of a galaxy is equally friendly to life. Near the crowded center of the Milky Way, stars are packed close together. Supernova explosions occur more frequently, and the supermassive black hole at the core, Sagittarius A star, exerts strong gravitational influence over its surroundings. In contrast, the outer regions of the galaxy are quieter. Our solar system orbits roughly 26,000 light-years from the galactic center, inside the relatively calm disk of the Milky Way. In this region, catastrophic stellar events occur less often, and planetary systems can remain stable for billions of years. That stability matters. Complex life requires immense stretches of time to evolve. If nearby supernovae or gamma-ray bursts occurred too frequently, planetary environments could be repeatedly disrupted before life had the chance to develop. Earth appears to occupy a fortunate location, far enough from the dangerous activity near the galactic core, yet close enough to regions where heavy elements from ancient supernovae made rocky planets possible. It is a narrow balance. Too close to the center, and radiation becomes overwhelming. Too far away, and the ingredients needed to build planets may be scarce. Somewhere in between lies a quiet corridor of space, where stability can last for billions of years. And within that quiet corridor, one small planet formed oceans, atmospheres, and eventually life capable of looking back at the universe that created it. When we search for the most dangerous places in the cosmos, we discover something equally remarkable. The places where life can safely exist may be among the rarest environments of all.